Okay, we're still on section 1, theory of heat, in unit 3, refrigeration and refrigerants, page 52. Screw compressor is popular for use in low temperature refrigeration applications. The important thing to remember is that a compressor performs the same function no matter what type it is. For now, it can be thought of as a component that increases the pressure in the system and moves the vapor refrigerant from the low pressure side to the high pressure side into the condenser. 3.9. The condenser. The condenser is a heat transfer surface that rejects both sensible, measurable, and latent, hidden, heat from the refrigeration system. This rejected heat is a combination of the heat absorbed by the evaporator, the heat generated and concentrated in the compressor, and any heat absorbed by the refrigerant in the suction line before it enters the compressor. The condenser receives the hot discharge gas after it leaves the compressor through the short pipe called the hot gas line, which connects the outlet of the compressor to the inlet of the condenser. Figure 3.27. As you can see, the discharge line connects the outlet of the compressor to the inlet of the condenser. This line is also referred to as the discharge line. The hot gas is forced into the top of the condenser coil by the compressor. The discharge gas from the compressor is a high-pressure, high-temperature superheated vapor. The temperature of the hot gas from the compressor can be in the 200 Fahrenheit range and will change depending on the surrounding temperatures and the system application. The refrigerant at the outlet of the compressor does not follow a temperature-pressure relationship. This is because the refrigerant is 100% vapor and superheated. The high side pressure reading of 446 psig in figure 3.28, subcooled liquid at the outlet of the condenser. As you can see, we have suction gas from the evaporator. Then it gets discharged out. It's at 446 psig, 200 Fahrenheit gas from the compressor. Our refrigerant is R410A. It goes into the condenser. At 125 degrees Fahrenheit is the first point of liquid. It stays at 125. Then finally, near the end, it drops down to 120 degrees Fahrenheit. And then as it's leaving, it's 110 degrees Fahrenheit. The subcooled liquid to the expansion valve. 100% saturated liquid. Liquid subcooling starts when any more sensible heat is lost. The outside air is 95 degrees Fahrenheit. Okay, that's a nice diagram. Figure 3.28 corresponds to the 125 degree Fahrenheit condenser saturation temperature, which is the temperature at which the refrigerant will begin to condense from a vapor into a liquid. The vapor pressure of 446 psig, read by the high side gauge, is actually coming from the condenser. The vapor pressure is often referred to as head pressure, high side pressure, discharge pressure, or condensing pressure in the HVAC/R industry. The 200 degree Fahrenheit gas temperature coming out of the compressor is superheated by 75 degrees, which is 200 degrees Fahrenheit minus 125 degrees Fahrenheit, and again cannot have a temperature/pressure relationship. Therefore, the hot vapor must first cool or de-superheat 75 degrees Fahrenheit before it can begin to condense. The gas leaving the compressor, flowing through the discharge line and entering the condenser, is so hot compared with the surrounding air that a heat exchange between the hot gas and the surrounding air begins to occur immediately. The air being passed over the condenser is 95 degrees Fahrenheit compared to the near 200 degrees Fahrenheit gas entering the condenser. As the gas moves through the condenser, it begins to give up sensible heat to the surrounding air, which causes a drop in gas temperature. The gas keeps cooling off, or de-superheating, until it reaches the condensing temperature of 125 degrees Fahrenheit. When the change of the state begins to occur, the change of state begins slowly at first, with small amounts of vapor changing to liquid, and gets faster as the vapor-liquid mixture moves through the condenser. This change from vapor to liquid happens at the condensing saturation temperature and pressure of 125 degrees Fahrenheit and 446 psig, respectively. This is a latent heat process, meaning that even though heat in BTU is being rejected from the refrigerant, the temperature is staying constant at 125 degrees Fahrenheit. Note, this process of constant temperature occurring during the change of state does not occur for some of the newer blended refrigerants that have a temperature glide. When the condensing refrigerant gets about 90% of the way through the condenser, the refrigerant in the pipe becomes pure saturated liquid. If any more heat is removed from the 100% saturated liquid, it will go through a sensible heat rejection process because no more vapor is left to condense. This causes the liquid to drop below the condensing saturation temperature of 125 degrees Fahrenheit. Liquid cooler than the condensing saturation temperature is called subcooled liquid, figure 3.28. We already looked at that. It's good to know though, subcooled liquid. That's what comes out of the condenser. The amount of subcooling in the condenser is the difference between the temperature of the refrigerant at the outlet of the condenser and the temperature at which the refrigerant condenses. Referring to figure 3.28, it can be seen that the refrigerant condenses at 125 degrees Fahrenheit and leaves the condenser at a temperature of 110 degrees Fahrenheit. This means that this condenser is operating with 15 degrees of subcooling. 125 minus 110 equals 15. Three important things may happen to the refrigerant in the condenser. 1. The hot gas from the compressor is de-superheated from the hot discharge temperature to the condensing temperature. Remember, the condensing temperature determines the head pressure. This is the sensible heat transfer. 2. The refrigerant is condensed from a vapor to a liquid. This is latent heat transfer. 3. The liquid refrigerant temperature may be lowered below the condensing temperature or subcooled. The refrigerant can usually be subcooled to between 10 degrees Fahrenheit and 20 degrees Fahrenheit below the condensing temperature, but is system dependent. Figure 3.28 shows that this is a sensible heat transfer. Many types of condensers are available, but all are designed to reject heat as they de-superheat, condense, and subcool. Very often, the condenser and the compressor are incorporated into a single piece of equipment called a condensing unit. Figure 3.29 shows some typical condensing units. And I'm allowed to look because it's a figure. So up top, we have a typical air-cooled condensing unit found on a split-type central air conditioning system. Has a solid-state control board, insulated jacket on the compressor for sound deadening and sweat prevention. Then below, we have an air-cooled hermetic condensing unit from a refrigeration system. Yeah, it's just all on one big plate. Alrighty, that's pages 52 and 53. I will see y'all tomorrow.